So good morning. So in this chapter we will see the numerical methods used for the resolution of f of x equals 0, where f is a continuous function defined on a given interval. Problems of the type f of x equals 0 are very common in physics. As a practical example, we'll give the example of an object falling vertically through the air and subjected to the viscous resistance of the air as well as the force of gravity. So assuming that the object has an initial height y0, so the height of the object after a time t can be modeled by the following equation. So if we want to find the time t such as the object hit the ground, we must solve a nonlinear equation here that is quite impossible to solve analytically. So for this reason, we have to employ numerical methods. And now I will present the table of contents of the chapter. So first we will discuss the existence and localization of solution for the problem f of x equals 0. And then we will present the most basic root searching method, which is the bisection method. Then the method of false position. Then the fixed point iteration method. And then the Newton-Raphson method, which is a special fixed point iteration method. And finally, the secant method, which is derived from the Newton-Raphson method. So consider that we have a function f that is a real function, continuous, on a closed interval ab. So if we have f of a, f of b negative, means one of or f of a positive and f of b negative or the contrary, then there exists at least one solution S, such as f of s equals 0. Now, additionally, if f of x is strictly monotonic on the interval, then there exists a unique solution S. For example, let's consider the following function, f of x equal x plus log x, on the interval 0, 1. Now, f of x is not defined on 0. So that's why the interval is open here. So, the limit x tends towards 0, f of x is equal to minus infinity, and f of 1 equals 1. Then there exists at least one solution in this interval. Now let's calculate the derivative f prime of x. So the derivative of x is 1, the derivative of log of x is 1 over x. So the log here is the Neperian logarithm. So basically this derivative is positive for the interval 0, 1. This means that there exists a unique solution S on this interval. Okay. Now I will present the bisection method, which is the most basic numerical root finding method, and it's based on the intermediate value theorem. It consists on bisecting the interval AB to smaller and smaller interval. So the principle of the bisection method consists of, so if you have an interval AB such as f of a, f of b is negative, so we construct the point C equals a plus b over 2. Then we check if f of a, f of c is negative. In this case, b equals c. If f of a, f of c is positive, like in this case, then a equals c. Like this, I reduce my interval from half. And then, again, I cut this interval in two, f the c. I check f of a, f of c is negative, yes in this case, then b equals c. Then I repeat the process, cut the interval in half, check f of a, f of c is negative or positive. Here it's positive, then a equals c. And I reduce in this fashion the interval a, b till the length of the interval b minus a is inferior to some precision epsilon that we specify. For example, epsilon is equal to 10 minus 6, 10 minus 5, etc. And now we will evaluate the number of steps required to reach a given precision epsilon. So, if the length of the interval is b minus a, after one iteration, the length will be reduced by a factor 2. So basically, it's b minus a over 2. After n step, the length will be b minus a over 2 power n. So we want that after n steps, the length of the interval is inferior to some precision epsilon that we specify. So solving this equation will give n superior or equal to log b minus a minus log of epsilon over log of 2. Okay? To find this expression, you just write 2 power n equal to exponential n log of 2, and then you take the logarithm and from the both sides, and you get this expression. Now, for example, if b minus a equals to 1 and epsilon equals to 10 minus 6, the number of iteration approximately is equal to 20. Now, the bisection method is relatively slow converging. When I say relatively, is compared to other methods that we will discuss, but it always works. There is no specific condition of convergence for the bisection algorithm. In order to implement a program numerically, it's important to know to draw the flowchart or the diagram of this algorithm. A flowchart represents the flow of instruction of the program. Now, we adopt these conventions for the different instruction. So, this shape will represent inputs or outputs of the program. The rectangular shape is for the process or the operations of the program. The diamond shape represents a condition and where a decision has to be made. And finally, this shape is to indicate the start and the end of the program. Now I'll present the flowchart for the bisection method in this case. So we start by defining the inputs of the problem, which are a, b, the function f, and the precision epsilon. And now we will implement a while loop. So while b minus a in absolute value is superior to epsilon, I make c equals a plus b over 2. And then we check if f of a, f of c is negative, then b equals c. If it's positive, then a equals c. And then Here we repeat the process till b minus a becomes inferior to epsilon. Then we exit the program, print the solution, and exit the program. So now I will show you the program for the bisection method. So first I defined a function f in a separate file. Of course, this file must be in the same folder than the main program for the bisection. So y equals x plus log x. So f of x return x plus log x. And now for the main program of the bisection, I define a and b. So because the function f diverges at the point 0, so I will take a value close to 0 but not exactly 0. So here I took 0, 0, 0, 0, 1. And I define here my precision epsilon, and the number of iteration that I will increment while I'm running the while loop. Now I do while the absolute value of b minus a is superior to epsilon, c equals a plus b over 2. If f of a, f of c negative, then b equals c, else a equals c, and I increment the number of steps. I calculate the number of steps required to reach this precision epsilon. And at the end, I print out the solution, which will be c, and the number of iteration, and I check if f of c is 0 or approximately 0 or not. Okay, so this is what I get. So this is my solution, 0.5671. The number of iteration is 20, which is exactly what we calculated before. When the length of interval is 1, then it takes 20 iteration for this precision. And this is the value of the function f at this point with this given precision. And now we will discuss the method of false position, which is called also regula falsi in Latin. So this method is similar to the bisection method, except in this case, instead of bisecting the interval AB in half, we construct the line passing through the points AF of A, BF of B, and we look at the intersection between this line and the x-axis. So this would be my point x here. And then similarly, I check if f of A, f of x is negative. If not, then A equals to x. If yes, then B equals to x. So in this case, f of A, f of x is positive, then A is equal to x. And then this is my new interval AB. And I repeat the process, construct the line passing through A and B, get the intersection here, x. I check if f of A, f of x, here it's positive, then A is equal to x. And I repeat the process again and again. And as you can see here, I reached the solution with almost 4 iterations. So I'm very close to the solution here. Okay. Now, we will derive the iteration for the false point method. So what we are looking for is the expression for the point capital X here. in function as a and b. Now, so the equation of the line is given by a0 plus a1x, such as y of a is equal to f of a, y of b is equal to f of b. Solving this system of equation gives a1, the slope, is equal to f of b minus f of a over b minus a. a0 is equal to b f of a minus a f of b over b minus a. And now this point x is given by y of x equals 0. So x is equal to minus a0 over a1, which gives a f of b minus b f of a over f of b minus f of a. The flowchart, or the algorithm for the false point method, is similar to the flowchart of the bisection method, except that in this case the difference is not only the expression for the point x, but also the fact that previously for the bisection method we used as criterion of convergence the lengths of the interval AB. Now, as you can see from the previous example, after a few iterations we reached a value for x that is close to the real solution, but the interval AB remains quite large. So as a criterion of convergence, we will choose as criterion of convergence the distance between the solution at step n plus 1 minus the solution at step n. Means the difference between the actual solution and the previous solution. So we start by defining the constants of the problem, a, b, the function f, epsilon, and d, which will be the distance between the actual solution and the previous solution of the next step. So we start by initializing d at some large value superior to epsilon, so we can enter the loop here. Okay. Now, before entering the loop, we initialize x1 equals a f of b minus b f of a over f of b minus f of a. So this will be the solution at the first step. And then we will calculate the solution of the next steps inside of the while loop. So we check if d is superior to epsilon. Okay, like I said, d will store the value of the difference between the previous solution and the actual solution. Now, if it's initialized at a value that is superior to epsilon, so we enter the loop. Now, we store the solution of the first step. So we make x equal x1. So this is the previous solution, because we will update the x1 here. Now we check f of x, f of a is negative. If it is, then b equals x. If no, then a equals x. And then I calculate the x1, which is the solution now at the next step, at the step 2 here. Okay? And then I calculate the difference in absolute between x1 minus x. And I check d superior to epsilon. If not, I repeat the process again and again till d becomes inferior to epsilon, and then I print the solution and exit the program. Now I will show you the program for the false position. So like we said, we define A, we define B, and I define the function f the same as before. We define the epsilon. This is the number of iterations. So I will start from 1 here because I will calculate my first iteration outside of the loop. And then I initialize D, some value superior to epsilon. Okay, I took here 10 times epsilon. You can take any value that is superior to your precision. And then I enter the loop. So while D is superior to x equals x1, if f of x, f of a negative, then b equals x, else a equals x. And then I calculate here x1 a f of b minus b f of a divided by b f of b minus f of a. Calculate the distance, increment the number of iteration, and at the end I display the number of iterations, the x1, and I check if f of x1 is close enough from 0. Now if I run the program for the false position, of course I get the same solution than before, but as you can see here, the number of iteration is larger than the bisection in this case, which is normally strange because the false position is normally a faster convergence method. It converges faster compared to the bisection. But the problem in this case comes from the fact that I started from a value a that is very small and close to 0 where the function diverge. So the initial value, the value for f of a is very negative, and the line will cross the x-axis at initial x that is very far away from the solution, and then it will move very slowly towards the solution. Now whereas here, if I raise a little bit the a and I run the program, so here I get the number of iteration equal 15. So of course the speed of convergence depends also on the initial estimates or the initial solution.